Well, good morning, everybody. Welcome to Rio de Janeiro and to IMPA. We begin our conference. We'll have some announcements during the days, and the program which you received is slightly not up to date, but there is an up-to-date program on the website of the conference, which will almost up-to-date program on the website, and that one will be updated. Whenever you have any questions, please feel free to ask me, Misha, one of the organizers, Alan, Matthew, Stefano. Where is Stefano? Stefano is there, and Plinio is arriving. Well, the first speaker today is Bena Tshishiku, who will talk about
hyperbolic manifolds, smooth structures, and group actions.
Excellent. Hyperbolic manifolds, smooth structures, and group actions. This one.
Okay. All right. So thanks to the organizers for the chance to speak. So let me start by telling you about the specific problem I'm interested in, which is an example of a Nielsen realization problem. So the setup, N will be a closed, oriented hyperbolic manifold of dimension N. N will be the dimension. And sigma will denote a homotopy N sphere. And so the manifold I'm going to consider is the connect sum of this hyperbolic manifold with the homotopy N sphere. And the Nielsen realization problem, so we have the diffeomorphism group of this manifold, which maps to symmetries of the fundamental group. So I'm going to write pi for pi1 of this manifold, which is the same as pi1 of the hyperbolic manifold. And the question is, if I have some subgroup G, symmetries of the fundamental group, can I promote this to a group of symmetries of the manifold? So does there exist? Like this. Okay, so some remarks. So first of all, so any finite subgroup of diffeomorphisms of a manifold like this injects into out of the fundamental group. So this question is really closely related to understanding group actions on this manifold. Any finite group action on a manifold like this is a solution to one of these lifting problems. I mean, okay, so that's the first comment. If for the manifold N itself, we know the answer by Moscow rigidity. So this splits because out of pi is isomorphic to the isometry group. And so that gives a splitting. This N connects some sigma. It's always homeomorphic to N, which is not so hard to see, but not necessarily diffeomorphic. Okay, so if I change diff to homeo here, then then n connect sum sigma is just n, and we know the problem, how it works for n. Okay, so this is really about the smooth structure. And then one more comment. So homotopy n spheres are, with the appropriate equivalence relation, are in bijection with isotopy classes of diffeomorphisms of the n-1 sphere. So it's the mapping class group of the n-1 sphere. This goes via clutching. So if you have a diffeomorphism of Sn-1, you can build a homotopy n sphere by taking two n disks and gluing them together along their boundary. And this is how you build all homotopy n spheres. So I'm going to write this group. It's typical to call this theta n, the group of homotopy n spheres. And
so you're supposed
yeah.
to dimension is at least 5?
Oh, yeah, right. Everything will be in higher dimensions. Yeah, so, yeah, right. I don't, I won't have anything to say in dimension 4, for example. Yeah, and this, yeah, this is maybe n not equal to 4. Thanks. So this is some finite group, finite abelian group. Milner and Crevere showed that. And so for example, theta 7 is isomorphic to z mod 28z. And it's generated by the following. So sigma is okay, so this variety in C5, defined by these polynomials, gives you a homotopy 7 sphere, which is, so it's homeomorphic but not diffeomorphic to S7, and it turns out that it generates this group. Okay, so that's an example. Okay. Let me now give some context, maybe some motivation for this problem. Right. So let me change the setting slightly. So M now I'll take to be a closed Riemannian manifold with negative curvature. And again, I'm going to consider the realization problem. But I'd like to contrast several versions of this. So you can ask whether you can lift it's a finite subgroup of out of pi 1 to homeomorphisms or to diffeomorphisms. Or maybe the best thing you might ask for is isometries with respect to some negatively curved metric. Right, so this strongest version of the question, this was originally asked by Nielsen, hence Nielsen realization in the case of surfaces. And maybe even you want hyperbolic metric in that case. And then in this more general setting, it was asked by Shane and Yao. And, well, the answer is yes, at least if M is hyperbolic. Just asking for a lift into homeo, this is closely related to, well, things related to the Borel conjecture. And I want to say a bit about that. So this will provide a bit of motivation for the results. Yeah.
Condition means that if M possesses some hyperbolic matrix, then there always exists some other, probably different negatively curved metric which realizes the final subgroup, right?
Yes. So in dimension 2, this is Kirchhoff's theorem. And then in dimension at least 3, this follows from Mostow rigidity. In dimension at least 3, the hyperbolic metric's unique, so it's that one. But yeah.
But this metric need not be hyperbolic. This is upstairs isometry. M sum K minus 0.
Maybe I misunderstand the question. So M, for a hyperbolic manifold, you can take the metric to be hyperbolic.
Okay.
Yeah. That's, yeah. Okay. Okay. Right, so I was saying there's this theme, which I'll call a Borel theme, which is so topological properties of an aspherical, closed aspherical M are determined by the fundamental group. Okay, and I guess writing it like this makes it sound like it's a fact, but it's a theme. Maybe I should put like a question mark here. To what extent is this true? So like one instance of this is the Borel conjecture, which predicts that the manifold, a closed aspherical manifold, is determined up to homeomorphism just by its fundamental group. Let me give one example related to Nielsen realization. So Nielsen realization for Seifert fibered spaces. This will give some indication of the type of answers we want to the question on the far board there. So let's consider M a 3 manifold, which fibers as a circle bundle over a surface. So this is a surface. Let's say genus at least 2 for simplicity. So the realization problem, if you have some subgroup of out of pi 1, right, so we want to understand when this is realized into homeo or diffeo. Let me say homeo. And well, okay, so the first thing one can consider is, so over out you have this extension which you can pull back to G. And right, so as it relates to the realization problem, if this exists, if a lift exists, then what you get is, well, a slightly different extension. Where here the kernel is pi1 of m. So if you have a group of homeomorphisms, you can consider lifts to the universal cover, and that will give you an extension like this. And this extension, well, will induce this one. So here the kernel is just pi1 of the surface. So this is like star is induced. Oh, so this is, if I call this star, this is induced by an extension like this. And it's a theorem of Zimmerman that this is an if and only if. And the main thing I want to point out about this result is, so on the right-hand side here, this is just something phrased in terms of the fundamental group. Okay, so that's kind of what the Borel theme says you should look for. So you can determine if G is realized just by looking at something related to the fundamental group, this extension here. And in fact, this is given by some obstruction in the third group cohomology of this finite group. Here G should be finite. Okay, anyway. So coming back here, for M negatively curved, this is, we don't know any obstructions, but so this is open in general. Well, I'll mention, so the most recent work related to this is due to Davis and Luke. But we don't, yeah, so it's open in general. Okay, and now let me return to the Diffio case. So here, in this case, it turns out the answer is no. You can't always lift. This was first observed by Farrell and Jones, who showed for M, one of these manifolds, N connects some sigma over here. Hyperbolic connects some homotopy sphere. This homomorphism from diff to out is not necessarily surjective. Okay, so in this, for this manifold, out of pi is just a finite group, so it not being surjective means you can't split. You can't lift the whole group. Okay. All right, so the main thing I'd like to focus on is understanding what happens here a bit more thoroughly. And maybe just I'll state as a question or a problem is to characterize when this homomorphism splits over subgroups in terms of the fundamental group and the choice of homotopy sphere. Okay, so this is maybe, well, sort of in line with the Borel theme. You sort of know you can't just do it in terms of the fundamental group because, well, there's these different choices of the smooth structure, but maybe just a bit more information incorporating that smooth, or the homotopy sphere, you can give an answer. Okay, or to what extent can one do this?
Can I answer?
Yes, please.
Is out pi not finite?
So if n is at least 3, then out of pi is the isometry group, which is finite.
Okay, so then you're just talking about lifting all of it, or do you?
You can ask about lifting all of it or lifting subgroups. I mean, if you're given a subgroup, I mean, yeah, I mean, what we'll see is some subgroups will lift, some will not. We'd like to understand which, when, what happens. Yeah. Okay. Other questions at this point? Okay, so for the most part, I'm going to be interested in obstructions to lifting and trying to understand those. But let me start with the construction. Which is, so how to build lifts sometimes. And the construction is equivariant connect sum. Let me say it this way. So the observation is this splits over G if the homotopy sphere sigma is divisible by the order of G in this group of homotopy spheres. So let me explain why this is true. So divisible means here we can write sigma as a connect sum. So the group operation is connect sum of G many copies of some other homotopy sphere. And if you can do that, then here's how you build a realization. Here's a cartoon. So here's N, and you have G. Well, G is in out of pi 1. But that's the isometry group of N. So G acts on N. And well, you can pick some point with a free orbit and then connect some with omega along this orbit. Here's omega, omega, omega. So now this is N connects some omega G times, which is diffeomorphic to N connects some sigma, and G obviously acts here. Okay, so this is a way to get some examples. And like I said, the main thing I'm going to focus on is obstructions. Obstructions. And maybe one other thing I want to remark at this point is that well, out of pi can be any finite group. So this is the theorem of Bellow, Lipetsky, and Lubatsky. So in any dimension, every finite group is the isometry group of some hyperbolic manifold. And so, well, this is saying there's lots of, I mean, this is interesting. I mean, there's lots of groups to put here. Okay. All right. All right, so now I'll turn to the first obstruction, which is related to this result of Farrell and Jones. So let me say what they did, what they show more precisely. Okay, so obstruction 1. Which is, well, if you want to lift G, then G had better be in the image of this map. So it's a simple observation. But the surprising thing is perhaps that this is not always surjective. So what Farrell and Jones show is that, well, so if N is stably parallelizable, which is the tangent bundle is stably trivial, then if this, oh, and I also want to assume one more thing, that N has an orientation reversing diffeomorphism, isometry, or diffeo. Oh, which is the same, so that's the same as saying N is orientation preservingly diffeomorphic to N with the opposite orientation. So I'm just going to write this because it's a little bit shorter. Okay, so that's the assumption. Then the statement is if N connects some sigma also has an orientation reversing diffeomorphism, then this implies that sigma has an orientation reversing diffeomorphism. Okay, and then this is the same as saying that sigma has order 2. In this group theta n. Okay, so like theta 7 is Z mod 28Z. Most elements in that group don't have order 2, so that gives you some examples. Okay, so that's what Farrell and Jones show. In contrast, let me remark that if you just restrict to orientation preserving things, then this map is always surjective. And then let me also mention that, well, this property is somehow special to this choice of these sorts of smooth structures. So a theorem Mauricio and I proved is that so for the smoothings where, so instead, yeah, so like so connect some with a homotopy sphere, you think about, you remove a disk and then you glue it back in a different way. Another thing you could do, you could remove a small neighborhood of a geodesic and then glue that back using, so here theta is in diff S n minus 2. So call this n. It depends on its choice of geodesic, gamma. And this gluing map phi. So for these smoothings, the image of the diffeomorphism group in out of pi, so the size of this can be arbitrarily large. Okay. All right, so I mean, this is one reason maybe to just focus on these examples, because then at least you know that this map is surjective for orientation preserving things. Okay, so I want to say something about how Farrell and Jones' argument works to give you some idea for what sort of goes into this. And similar kind of techniques are involved in what Mauricio and I do. So here's some ingredients of the Farrell and Jones argument. So in short, one uses rigidity to reduce the problem to some smoothing theory computations. So the rigidity, so the first ingredient is Mostow and topological rigidity. Which is to say the Borel conjecture for hyperbolic manifolds, which was proved by Farrell and Jones. What that buys you in this situation is if you start with this assumption that N has an orientation reversing diffeomorphism, then this implies that from this you can conclude that these two smooth manifolds, N connects some sigma and N connects some sigma with the opposite orientation, are concordant, which is to say that there's a smooth structure on N times 0, 1, which restricts to these two boundary components as these two smooth structures. Okay, so, well, yeah, I just want to give you some flavor, so let me not explain this implication. But this is what rigidity gives you. And so then the next ingredient is smoothing theory. Right, so this will come up later, so let me set up some notation. So smooth N, I'll write for, these are smooth structures on N up to concordance. And, well, the thing one wants to understand for the purposes of the Farrell and Jones argument is, so there's a map from theta n, which is identified with smooth structures on Sn, into the smoothings of n, given that sends sigma to n connects some sigma. And, well, you want to know, yeah, so at this point we have these two smoothings are concordant. We'd like to get to sigma and sigma bar being diffeomorphic, or concordant is just as good, and so we'd like to know that this map is injective. And so it turns out this is injective if, at least if n is stably parallelizable. So that's where that assumption comes in. Okay, so, well, maybe this is all I'll say about the argument. Well, yeah, so this, or maybe, let me say, so then what you get, so from knowing these are concordant, then you conclude that sigma and sigma bar are concordant, which implies that they're diffeomorphic orientation preservingly by like the H-cobordism theorem. Okay. So that's the Farrell and Jones argument. And right. I won't, I think, have time, or I won't focus on the proofs and what follows, but this is kind of a general outline. One uses rigidity theorems to reduce to some smoothing theory computation. And maybe the thing I'll emphasize that, so this smoothing, the smoothing's on N. This is in bijection with, so it's represented by maps into a certain space, top mod O. Top mod O is an infinite loop space. So this is an abelian group. So this is a finite abelian group, but yeah, but you should not think that this is something easy to understand. It's a finite abelian group. It's hard to compute for hyperbolic manifolds. And so, well, right, you use rigidity to reduce to some smoothing theory computation, and then you have to work hard to do something there. Okay. All right. Questions at this point? Okay, let me move on to a second obstruction. Okay, so now, given this lemma here, well, I'm going to restrict to orientation preserving things. So at least I know that the map from diff to out is surjective. And the second obstruction comes from noting that this homomorphism factors through the mapping class group. Okay, so the first thing you need, well, an intermediate problem is to determine if this homomorphism from the mapping class group to out of pi splits. So this is just pi, the group of components. Okay, so that raises the question of, well, what is this mapping class group? So so this is work in progress, what I'll tell you next with Mauricio. Right, so the first thing is, well, okay, so first of all, this map is surjective, as discussed previously. Oh, pi 1, that's just pi. Pi is pi 1 of n, sorry. So there's an exact sequence like this, and the kernel can be identified with the kernel of the map from the mapping class group of of the standard smooth structure on n to out of pi. And this is computed by Hatcher and Farrell and Jones. So this is isomorphic to a group like this. Okay, so you have infinite direct sum of Z mod 2. So this group in particular is not finitely generated. And then something to do with smoothings of n times S1. Okay. Right, so this is an abelian group. So to understand this extension, well, there's an Euler class which classifies this extension, which lives in H2 of out of pi with coefficients in this group K. Yes?
Can you say a word about how this infinite product shows up?
Oh, this one?
Yeah.
Yeah, so this, well, the one word answer, this comes from pseudo-isotopy. These, from pseudo-isotopies. You can think of this roughly as the group ring of the fundamental group with Z mod 2 coefficients. It's not exactly that, but morally, for every element of pi 1, you can do some local, some diffmorphism supported, even homeo supported locally on that loop. And these things are homotopically trivial, but they're not, they're homotopic to identity, but they're not isotopic to identity. They're also not pseudo-isotopic to identity. Yeah. Oh, direct sum. Yeah. Yes. Yeah. Right. Okay. Right. All right. So it turns out one can understand something about this Euler class. So there's a formula. Like this. And before I explain what this means, well, let me just say in advance, this is identifying the Euler class in terms of the fundamental group and the homotopy sphere. So it's, in terms of the question I wrote earlier, something along those lines of understanding. I mean, this is the obstruction to splitting, so somehow that depends in a concrete way on pi and sigma. Okay, and how precisely? Right, so yeah, so E aught tilde. So this is the Euler class of a certain other extension. Oh, and I realized that I'm saying the wrong thing. So sorry, I need to change this slightly. Okay, so for what I'm about to say, this is the based mapping class group. So yeah, so ultimately to understand the mapping class group, it's helpful to first consider the base version. So I fixed some base point. And let me just tell you something about that. This is still correct. The Euler class here, this is going to be for aught. Okay, so the second Euler class, now the coefficients are Z mod 2Z. And the extension is, well, so it comes from hyperbolic geometry. So you have the automorphism group of pi, which maps to isometries of Hn. And then there's an extension of this of the isometry group, which is the universal cover. And I'll write ought tilde for the pullback extension. Okay, so that extension has an Euler class here, which I'm writing E ought tilde. And the Euler class that describes the mapping class group is pushed forward by, so now I sigma, this is a homomorphism from Z mod 2Z into K. And actually it factors through this smoothing part. And let me say briefly, well, let's see. Yeah, let me say briefly how that goes. So this homomorphism, it sends 1 to, so it's a smoothing of n times S1. And it connects some with a certain homotopy sphere, which I'm writing as eta sigma. And here eta is a homomorphism from theta n to theta n plus 1. So the dimension has increased by 1. And how does this work? So given a homotopy n sphere, you could construct a homotopy n plus 1 sphere as follows. So eta sigma, well, OK, so I want to think about this as pi 0 of diff Sn. And this will be, so the sphere twist about Sn minus 1 in sigma connect some sigma bar. OK, so the picture is here's, so this is Sn. And where the connect sum is performed, you have an n minus 1 sphere. And then, well, there's something like a Dane twist you can perform along this n minus 1 sphere, where you just do a family of rotations in a tubular neighborhood. And that gives you an element here. OK, so OK. OK, so it's maybe a little complicated, at least the first time you see it. But this identifies the Euler class of the extension that defines the base mapping class group. All right, so let me just mention a couple of corollaries of this. So the first thing I want to say is, so using this, you can show that this this homomorphism from mod to out, where here I'm dropping the base point, is not always split. And let's see, so you can do this when, so all right, so let me assume so I want to assume that n is stably parallelizable, and that n naught, and that n regularly covers a manifold n naught, which is not spin. And then there's an assumption that this eta sigma is not divisible by 2. And then with this, you can conclude that this homomorphism is not split. So this gives you, right, so regarding when you can satisfy these assumptions, so Deline and Sullivan showed every hyperbolic manifold has a stably parallelizable finite cover. Examples of hyperbolic manifolds which are not spin were constructed by Martelli, Riolo, and Slavic. So you can get this situation in all dimensions at least 4. And then this condition holds in infinitely many dimensions, starting with 8, but not every dimension above 8. So okay, so there's some examples. And while I'm, yeah, so related to this, let me mention some other work, related work. Which is joint with Mauricio and Manuel Kranek and Sander Coopers, which, so using the same ideas, you can do the same, so look at exotic tori and this splitting problem. And we determined that this homomorphism splits. So now we have SL and Z out of pi, now infinite. This splits if and only if this eta of sigma is divisible by 2. And when it's not divisible by 2, so in infinitely many dimensions it's divisible, and then there's an infinite number of dimensions where it's not divisible by 2. When it's not divisible by 2, we could show something slightly stronger, which is that every homomorphism from SLNZ to this, to diff of the exotic, if Tn connects some sigma, is trivial. So this is like some Zimmer program type of statement. Not only does it not split, but there's no homomorphism at all. Okay. Okay, so let me wrap up. Let me yeah, okay, so let me finish by just stating one question. Which is related to, which is just a question in hyperbolic geometry. So maybe someone here can say something about it. So well, the short version is it possible to compute H2 out of pi with coefficients in the homology, the first homology, it's Z mod K, Z mod, let's say Z mod L coefficients. So as always, N is a hyperbolic manifold. So, and I mean, this is like the isometry group. Isom of N with coefficients in H1. This problem comes up in terms of understanding the extension where you drop the base point. And well, maybe I'll mention, so if you go to dimension 2, there's work of Morita who shows that for a surface, H2 of out of pi. Okay, so now this is the mapping class group, so it's slightly different. With coefficients in H1, the homology, first homology of the surface, this is isomorphic to cyclic of order the Euler characteristic. And it's generated by, and for this I should say G is sufficiently large, by the most obvious extension to write down would be this one with the right kernel. So this is the commutator subgroup pi prime. So this is H1 of SG. And this extension generates H2, at least if G is large enough. And so, yeah, if it would be interesting, helpful if there was some analog of this in higher dimensions. Okay, I'll stop there. Thanks.